Okay, for this final section in this unit that we've been talking a lot about different types of quadrilaterals, and we have one more that we need to get through today. I've kind of talked about this one just briefly in that I said it's not necessarily the same as the family of quadrilaterals that we saw last week. So we talked about how rectangles, rhombus, squares, all of those are considered parallelograms. And if you remember, like last week on Thursday when we talked about how all the shapes are kind of related and they kind of make like a little family of shapes, I said that we still have to talk about the trapezoid, but the trapezoid is a little bit different than all those other four. So we can't really include it in with those four because it kind of does its own thing. So what a trapezoid technically is it is a quadrilateral with one set of parallel sides. So kind of like a parallelogram had one pair of, or had two pairs of parallel lines, and so did a rectangle and a square and a rhombus. A trapezoid has one pair of parallel sides, but not two. So we can't say that both pairs of opposite sides would be parallel on a trapezoid. Usually the parallel sides are going to be known as your bases on your trapezoid. And so if a trapezoid is sitting maybe what we would call like upright, that would mean that it's on one of the bases. And so then the other base would just be the side that's directly across from it. Now, they won't always be that way. Sometimes they'll try to trick you by putting the trapezoid in a different position. So we do just want to kind of, before we even begin a problem, look at the picture, make sure that we can identify the parallel sides. Once we have the parallel sides identified, then we're going to kind of start talking about properties that the trapezoid might have with its angles and with the other non-parallel sides. Okay, so as we kind of go through some problems today, we're going to be just kind of discussing and seeing how these new properties work and be able to solve for missing pieces with that. So if you look at these first two, I would just start by recognizing what sides would be your bases or what sides would be your parallel sides. So it might even be wise for some of you to mark that on your picture. Like when I look at one, UV and TW look like they would be the parallel sides. Because if I extend these out, and even if I just do that with a highlighter here, if I extend these sides out, if it'll let me here. Maybe I'll just try to do it with a pen. If I extend these sides out here, those would be your parallel sides. Okay, so on top and on bottom, I'm just going to put like a little arrow on them to just kind of remind myself here that like those are my parallel sides. Okay, so if you think about some of those properties that we saw last week, they're still going to hold true for our trapezoid. Like we have these parallel sides, which would mean the 137 and like where the question mark is, those would be those same side interior angles. And so if you remember from last week, we said that those same side angles add to 180. They're still going to do that on a trapezoid here. So the 137 and the question mark, whatever that is going to add to 180. So to find how much the question mark is, I'm going to take 180 minus 137, and that would leave me with 43. And so that would be this angle right there. Now, the difference is that the 137 and the 43 are not going to necessarily translate over to these angles here, okay? They're not going to match. So I don't want you to make that misconception. Those would be two different angles, but they would also still add to 180. And we could really go through and like find them if we really wanted to, but I'm not really too worried about that right now. Now, if you look at number 2, we have the same kind of issue happening here. We've got the top and the bottom would be your parallel sides again. And so the 115 and the 2x plus 41 should also add to 180. So this time, because I have an x, I'm going to have to solve for that. And if they wanted me to, I could then plug it back in to actually find the angle. They just want me to solve for x, so I don't need to take it that step further, but I could if they asked me to. So I'm just going to set this up where it says 2x plus 41 plus the 115 equals 180. And then you're going to solve for x. Why don't you guys take a minute and go ahead and do that? Okay, you should have added your 41 and 115 first and got 156, and then you subtract that from 180. That leaves you with 24. Divide by 2, you get 12. Now, if you wanted to double check your answer here, if you plug 12 in, so you take 2 times 12 and you add 41, that should be 65. And then if you add 115 plus 65, that should be 180. So just like we've had problems before where we've checked our answer, it's really easy to do that. Doesn't take much time. So on like your test day, if you have some extra time before you hand it in, it might be wise to go and double check your work. All right, now if you go down to these next couple of problems, we're still dealing with trapezoids, but notice how those non-parallel sides here have markings on them. So my parallel sides are still going to be for both of these, the top and the bottom, because those would be my sides that will never cross. Now the other sides are not parallel to each other because they are like slowly, maybe on that first one, they're slowly looking like they're going to eventually converge at the top. Now it's a little harder to see that just because they are so close to being parallel, but they are a little bit offset. Now 4 is a little bit more obvious to see that left and right sides, those are definitely not parallel. If I kept extending them, they would eventually meet. Okay, but it's good that we can still identify that. Now, what do those markings tell us is happening here with these sides? It means that they're congruent sides, right? So if I look at my trapezoid and if I have those two non-parallel sides marked so that they're congruent, this is technically then called an isosceles trapezoid. Just like we had an isosceles triangle where we had two sides that were the same terminology is used for a trapezoid. Now, trapezoid is still quadrilateral, so it still has those 4 sides, but if 2 out of the 4 are the same, then we would call this an isosceles trapezoid. So one of the properties I want to focus on with an isosceles trapezoid is that they have base angles, just like an isosceles triangle had base angles. Do you guys remember how you would find the base angles? They should be directly across from those sides. So the base angles that are across from those congruent sides, if you remember on a triangle, when we had our isosceles triangle and these two sides were the same, then these two base angles were also the same. Well, the same thing is going to apply to an isosceles trapezoid. If you have the base angles that are across from those sides, then they are going to be congruent. So if I look at my pictures here, I need to figure out how much this question mark is on number 3. I have a 94 up here by F. I could almost consider that this is across from that side, like if I just draw an arrow. So then if I go across from that other congruent side, so I'm looking up at E and F, those would be one pair of base angles. Those should be the same amount. So I should be able to fill in that E is also 94. So if I wanted to figure out how much the question mark is, think back to what we were just doing. What should the 94 and the question mark do? They should still add to 180 because they're still same side angles. So I'm going to take 180 and subtract 94, and that would leave me with 86 degrees. So this angle is 86. How much is G? should also be 86. They didn't ask me for that, but you should be able to know that because of those base angles that we just talked about. Now, we really probably won't talk a whole bunch about this, but I did have a couple of you bring this up last week when we were kind of talking about parallelograms and rectangles and all of that. We were kind of going over like properties that you kind of already knew about those shapes. And at least one person in all my classes said that the four angles instead of a quadrilateral equal 360 degrees. Okay, that's not something that we've talked about exclusively in here, but that is a true statement. So these four angles, 94, 94, 86, and 86, if I add those all together, I should get 360 degrees. So just maybe another little piece of information that you could add to kind of your already growing list of all these things that we know about these quadrilaterals is that those four angles inside of there should always add up to 360. So again, that would be a really easy way to check that you have the right angle measurements in your pictures. If you add them all up, you get 360. Okay, so now if you look at number 4, we're still dealing with an isosceles trapezoid. What's the relationship between angle V and angle Y that they have marked there? They're congruent because they're the base angles. They're across from those dashes. Just like W and X on the top, those would be the other pair of base angles and they would be congruent too. So how should I set this up to solve for X? I should set them equal to each other. Good. So I'm going to do that and then let's go ahead and solve this. What would you guys do first? Good. So now we have 14x equals 56. And then what? And we get 4. And again, if we check that, if we take 14 times 4, that's 56, minus 1 is 55. That makes sense because we knew that those two bottom angles had to be the same. Okay, so base angles on an isosceles trapezoid are always going to be congruent to each other. Now, if you go down to the next couple of problems, 5 and 6, we're still dealing with an isosceles trapezoid here because those sides are still marked. But we have another little property to add here. So let's add another little note. We're still talking about the isosceles trapezoid. And so this is talking about the diagonals because if you kind of read the directions here, it's asking about the length of a diagonal. Over here, it's asking us to solve for x, which if we look at the picture and we look at what they're giving us, they're talking about the diagonals. When you have an isosceles trapezoid, your diagonals are going to be congruent. These things that we've been talking about for numbers 3 and then now here to 6 only apply to isosceles trapezoids. Not all trapezoids are going to do this. So if you don't see that those non-parallel sides are marked as congruent, you cannot use these properties for just any regular old trapezoid. So even if I come back up here, 1 and 2 are not isosceles trapezoids. Okay, so like this angle here, T, and this angle here, which we found earlier, those would not be congruent to each other because they are not on an isosceles trapezoid. If I drew in the diagonals here, if I connected T to V and U to W, I'm hoping you can even just kind of see from my lines that I just drew, those are not the same length. Like UW is a little bit longer than TV is. So these properties only apply to these problems where those markings are present on the sides. Okay? So now if we look down here, we just talked about how diagonals are congruent to each other. So for number 5, if C to E, which is one of the diagonals, that whole thing is 20, how much should be DB? Should just be 20, right? Because we know that those diagonals should be congruent. Okay? Now if you look over at 6, EG, that's one of the diagonals, they're saying that's 24. FH is the other diagonal. They're giving me that expression 4x minus 8. How would I set this up to solve for x? Good. We should just set them equal to each other. We know that the diagonals are congruent, so you just pop an equal sign in between them. Okay, go ahead and solve for x there. You should have gotten 8. And again, really easy to check your work. You take 2 times 8, subtract 8 from that. I'm just plugging it back into FH. You should end at 24. It makes sense. Those diagonals should be equal to each other. Okay? So again, I just want to clarify those 2 things that we just talked about only apply to trapezoids that look like those last 4 where they have those markings on the sides. If you don't see those markings, then you can't use those properties to help you solve it. You have to either go back to what we were talking about at the very beginning of class today, okay, or maybe you'll have something that looks like these last 2. These last 2 are dealing with mid-segments. We've talked about mid-segments before on triangles, okay, just like we talked about isosceles triangles, and now we talked about isosceles trapezoids. We've talked about the mid-segments on triangles. Now we're going to talk about mid-segments on the trapezoid. If we want to figure out what the mid-segment would be, remember mid-segment meant middle. So like on a triangle, we had the mid-segment, we had the middle of 2 of the sides that were being connected. That's kind of happening here. We have like the midpoint of the non-parallel sides are being connected, and we're trying to figure out what that length would be. If you remember when we did that for the triangles, we said that the mid-segment was always half of the side that it's parallel to. Trapezoids is a little bit different. You can't just take half of one of the sides. You have to kind of look at both of the bases together. So we're going to actually average this out. We're going to add the base lengths together and then divide by 2. That'd be the same thing as finding the average. So like on this first one, I'm going to take 15 plus 27, and then we're going to divide that by 2. And so that should come out to be 21. And so that would be your question mark here, 21. Now, before we go on to number 8, can anyone see some kind of connection with these 3 numbers, like 15 to 21, 21 to 27? They're increasing by how much? 6 each time, right? 15 plus 6 is 21. 21 plus 6 is 27. Okay? That's always going to occur when you're dealing with mid-segments. I'm not saying it's always going to add up to 6. Like you're not adding 6 every time. But you're going to be adding the same amount every time when you go from one base to the mid-segment to the next base. Okay? And so you could start at like the top and add numbers, or you could start with the longer base and then subtract and like kind of work your way backwards if you needed to as well. So if you look at number 8, there's 2 ways that we could go about doing this one. Like we could set up an equation if we wanted to, where we don't know what this side is, where the question mark is. So we could call that x if we wanted to. And you could do x plus 20 divided by 2, because we'd still be finding the average, but this time we know what the average came out to be. We know it came out to be 24. Okay, that would be one way. But since we've kind of discovered this little bit of like a shortcut, I would think instead, what happened from 20 to 24? They added 4, right? So we would add 4 more here, and what would we get? 28. Okay, if you were to go about it over here with like the average, we would solve this by multiplying by 2. And so you'd have x plus 20 equals 48, and then you'd subtract 20. And look, you get the same answer that I just got. That side is just maybe a little bit longer of a process. If you didn't have like just numbers, maybe you were given just total expressions, like something with all these x's, and they didn't just like clear out, give you the numbers, then you might have to set it up as an equation like that. But if they're giving you numbers, you can just use that shortcut to help you figure out whatever piece is missing. Just make sure that it makes sense. So for example, like if they had given this side already as 28 up here, make sure you understand that if you work your way down, then you're subtracting 4 each time. It's not 28 plus 4 got you 24 and then plus 4 got you 20. You're actually subtracting if you switch the direction there. All right. That concludes our section on trapezoids.